So now we will look at quality experimental data from a rubidium helium system similar to our DPAL, and so from ionic transport and collision processes in laser gases after McDaniel, 1977. Using quality experimental data, we find that the rubidium ion helium system closely represents the condition for DPAL gain cell. So assume from the experimental data presented here in this table by McDaniel that the ratio of the electric field to the number density of the neutral gas in the far left column at in our case T effective of 500 Kelvin, which is the closest match in temperature to a rubidium DPAL system, which is at 473 K. We obtain a terminal velocity of 8.02 times 10 to the 4 centimeter per second. So therefore, for rubidium ion, terminal velocity is 8.02 times 10 to the 4 centimeter per second in helium. We can then estimate, as we will do later, the diffusion of the rubidium ion through selected thin film oxides in centimeter squared per second by use of the electrical mobility equation. So next we introduce the electrical mobility equation. For a particle with electrical charge Q, its electrical mobility is related to its generalized mobility by the equation mu equal mu q sub q over q. The mu sub q is the ratio of the particle's terminal drift velocity to an applied electric field. Hence, the mobility equation and diffusion in the case of a charged particle is given as d equal mu sub q, the Boltzmann constant, times the temperature divided by the charge. And so when a charged particle in a gas or liquid is acted on by uniform electric field, it reaches a constant drift velocity of Vd equal mu times the electric field in equation 15.8. And so it depends on the magnitude of the electric field. Um, you now have uh, mu being the ratio of the drift velocity divided by the um, electric field relative to the mobility mu. The next slide shows electric field contribution from the high power laser, and it's the electric field produced by laser input into the selected thin film material. So we calculated the electric field in volts per meter versus the laser power in watts per meter, and what we end up with is curves for the behavior of the thin film, aluminum oxide, silicon dioxide, tantalum penoxide, zirconium dioxide, and titanium dioxide. As you can see, this relationship, as the higher the laser power increases, the electric field increases much more rapidly in silicon dioxide, followed by aluminum dioxide, followed by tantalum penoxide, zirconium dioxide, and titanium oxide. In addition, the electric fields are much higher with increasing laser power in silicon dioxide in essentially the same order. So the results for the thin film shown in the previous graphs, which were for the thin film oxides, which were based on electric field versus increasing laser power. There were calculations that were done using the quality experimental data from McDaniel, as you can see in the far right column, with the assumption of the uh, drift velocity being 8.02 times 10 to the 4. And so with that assumption, we can easily now calculate the electric field as with increasing laser power in the case of silicon dioxide. And the behavior is pretty much similar for all of the metal oxides, except that the changes in electric field are different with increasing laser power in terms of magnitude, with silicon dioxide being the highest as previously explained. So we'll skip through these slides and we'll come to rubidium ion mobility and diffusion versus the electric field. And so if we consider the rubidium helium system, what we're looking at is the rubidium ion mobility becoming dropping off asymptotically to with increasing electric field or increasing laser power, and the same happens also with the rubidium ion diffusion as you increase your laser power. That they both fall off. The rubidium ion mobility falls off a lot quicker than does the diffusion. Next slide, we will examine non-steady state condition with Fick's second law of diffusion and its prediction of how the concentration of the diffusing ion changes with time. And this is a very familiar equation where the error function of the position divided by 2 times the square root of the diffusivity or diffusion coefficient times time. And so uh, CS is the surface concentration of the element in the gas diffusing into the fused silica surface. CO is the initial uniform concentration of the element. Uh, the Cx is the concentration of the element at distance x from the surface at time t, and x equal distance from the surface. And d is the diffusivity or diffusion, and t's time. Earth is the mathematical function called the arrow function. In the next slide, we will next we will take a look at Einstein's contribution in terms of the Stokes-Einstein relation. Irish scientist George Stokes showed that a particle of radius r moving with a velocity v in a viscous medium experiences a frictional force F equals 6 pi r eta nu. Assuming that the same relation applies to particle on an atomic scale, then we can, by means of the Nernst-Einstein equation, the diffusivity sub uh, eta equal the Boltzmann constant time temperature divided by 6 pi r eta nu. This equation relates the viscosity of a fluid to some viscosity diffusion coefficient. Although our thin film material interests are solid, the argument can be made that they're also highly viscous fluids, and they're d sub eta calculated also. So even though there is a difference between the fixed law diffusion coefficient and this d sub nu, d sub eta. So now we take a look at the Nernst-Einstein equation. The Typically, monovalent cations are the most mobile species in oxide glasses, followed by divalent cations, which are magnitude slower. For this reason, the majority of diffusion data on oxide glasses pertain to diffusion of monovalent modifier cations. If only one type of mobile cation is present in the glass, its diffusion coefficient can be deduced from sigma dc, which is its conductivity via the Nernst-Einstein equation. So as you can see in 16.4, where N sub ion is the number density of the mobile ions and Q the charge of each ion. And M is the atomic mass of the uh, in applying the Nernst-Einstein equation to the thin film group that we're looking at, we find that we can calculate the diffusivity or diffusion, and we did so with silicon dioxide being at 1.47 10 to the minus 4 centimeters squared per second, zirconium dioxide at 1.77 10 to the minus 2, tantalum pentoxide at 4.71 10 to the 12, aluminum oxide at 1.47, and titanium dioxide at 1.47 10 to the 6. So from these set of data, um, it's possible to believe. I think the biggest uncertainty is with the conductivity, the DC conductivity, which could be actually quite different even for a particular thin film. So this just kind of gives you some idea as to uh, what kind of diffusion to expect of the rubidium ion through these particular thin film. And tantalum pentoxide is shown to actually have the highest predicted DC conductivity in terms of diffusivity and or diffusion, and you could see that silicon dioxide will tend to have the lowest, and zirconium dioxide somewhere in between, and titanium dioxide and aluminum dioxide.